So the question here says 212 Bi decays with an emission of an alpha particle. The resulting nuclide emits a beta particle to give an element. Now we got to find out that element. Okay. Now herein, again for the solution, as we will see, I've written this is the mass number and this is the atomic number for Bi. So if it is undergoing a alpha particle emission, that means its mass number will be reduced by 4 units and its atomic number is going to be reduced by 2 units. So if we say this is the element X, now after doing the math, what we find is that it will have a mass number of 208 and the atomic number will be 81, and the element having the atomic number 81 is going to be thallium. Okay. Now here, further this particular thallium is undergoing a beta decay. Now a beta decay means obviously there is a neutron that is going to be converted to a proton and a beta particle. So if you write the beta particle, now you see it has a charge that is -1. All right. That means what we will do, we will add 1 unit of charge to the 1 unit of charge to the atomic number, which is 82. However, the mass number will remain unchanged because for the loss of a neutron, we already have compensated it by a proton. Okay, so now if we say that to be as y, then this gives us the mass number to be as 208 and your atomic number is going to be 82. So looking at the atomic number 82, we will say our answer is going to be lead. All right, now for the next question. Here it has been given, consider the following statements with respect to Jacobson's catalyst. It is used for epoxidation reaction, and it has manganese 3 complex, silane type ligand, cobalt 3 bromide complex, 1 nitrous or 2 naphthol type ligand, square pyramidal geometry, square pyramidal geometry. Choose, you got to choose the correct answer from the given options below. All right. Now for that, what is this Jacobson catalyst? It is basically a manganese coordinated to 2N, 2O, and a chlorine. So it is coordinated to 5 atoms. That means the coordination number over here is 5. Now, if you look at the charge, then what we will say, chlorine is having negative charge, chlorine is having negative charge, oxygen is having a negative charge, and the other oxygen also having a negative charge, and nitrogen is neutral over here. So we will say the over here the primary valency obviously is going to be 3, the oxidation number. So obviously this is a manganese 3 complex. All right, and we will say option C is incorrect because there is no cobalt in it. Next, this ligand that you see over here, okay. Now, if this is salicylaldehyde, then it combines with ethylene diamine, okay, in presence of small amount of catalyst acid, then it will form silane, and silane looks almost like this, okay. Okay, so if you remove the 2 protons, then we have a this is basically a tetradentate ligand with di-negative charge. So if you look at the ligand over here, this is also a amine, okay. Rather, this is cyclohexyldiamine, and this is also a derivatized salicylaldehyde, which has we will say tertiary butyl groups, okay. With respect to the C double bond O, or here it is C double bond N, it is having the tertiary butyl groups in the meta position, okay. So obviously this type of ligand is basically a derivative of silane. So we will say this is a silane type ligand. Now to predict the square pyramidal geometry, we will say it is square pyramid, okay. We can do it from VBT, that is valence bond theory. That would be the proper way of doing it. Or if you look at the uh, molecule over here itself, knowing the structure, you can see that this is the square base plane found by the nitrogen and the oxygen. Okay. And then we have a chlorine, which is in the axial part. So obviously this is having a square pyramidal geometry. So from here we can say that we have A, B, and E as the options correct. So obviously the answer should be 2. Now to predict the geometry, if you want to use VBT, that can also be done. Just keep remembering that N donors and O donors are obviously weak field ligands. So most cases this will be a high spin complex, and manganese is having a oxidation state of 3. That means it is a D4 system. So all you got to do is fill up the electrons in the d orbitals, that is the 3D, and then you fill in the 5 electrons coming from the ligands. So that will give you a combination of D, S, and 3p, that is dsp3, and this is the hybridization for a square pyramidal geometry. I hope that clarifies the answer that you had, question that you had. Now next is question number 34. This is the organic section over here now. We have to predict the correct order of basicity of the following compounds over here. Now we have A, B, and C. Now over here, if you look at this compound C, then please note I've drawn over here, it has 2 lone pairs and there are methyl groups. So obviously these lone pairs are going to repel among each other. Now it is in a fused ring. So there will be heavy steric repulsion between these lone pairs on the nitrogen atoms. And also there will be some steric hindrance coming from the methyl groups attached to the nitrogen atoms. Okay. So this is destable in this position. Now, if you protonate it, what happens is that the conjugate base, the conjugate base that is forming over here on protonation can also be stabilized by the another nitrogen atom via hydrogen bonding, as you can see over here. So here the free base is unstable, whereas the conjugate base is highly stable. So this is contributing the immense basicity of this particular compound. Okay, so C obviously over here will be our most basic in nature. So if we consider that to be the case, then obviously 1 and 2 are not in the options over here. So we got to choose from 3 and 4. Now, if we think among A and B, which is more basic, now basicity of amines depends on the availability of the lone pair on nitrogen and also of the stability of the conjugate acid that is formed rather. So this is the conjugate acid. So over here you can see the NME2 group, because of its plus M effect, is going to make this electron donate this electron to the benzene ring, and it is going to make this benzene ring more electron rich, which means that this particular lone pair on the nitrogen is more available. Whereas over here, since there are 2 benzene rings, okay, so this lone pair can be donated back to this nitrogen, and here also it can be donated back to this ring. So as such, there is no such because of this donation, as such, we can say that this lone pairs on these individual NMT groups are less available compared to when we compare with A, right? Because it is having the NMT group directly attached to the benzene ring. So obviously, we will say A is more basic than B, and as we have discussed before, that C is most basic among all these. So obviously, we will say the order would be C followed by A, then followed by B, and that would make the answer to be as over here 4. Okay. All right. Next. Over here, the question number 35 is regarding we have to choose the most suitable reagent to affect the following conversion. Now, over here, we have been given an unsaturated ketone, and there is also a non-conjugated double bond within the molecule. So this is the non-conjugated, whereas this is the conjugated part. Now, let's do the reactions. Okay. So if I take this molecule to be the central molecule over here, and if I add BH3THF, so obviously because there is a double bond, it will undergo hydroboration reaction. And we know for a hydroboration reaction, the hydride will obviously be added to the most substituted carbon over here. So H minus will be added here and BH2 will be added here. For this double bond, it will be H minus added here and BH2 will be added here. And that is how we have the molecule. Under the little bit presence of acid, right, what will happen is that these alkenes will be getting converted to, we will say, uh, the alkanes. Okay. Now, over here, this is a typical reaction. If we have, say, I'll discuss option 2 later on. In this case, over here, we have NaBH4 and CeCl3. Okay. Because there is a presence of CeCl3, all right. So in this case, what happens? Selectively, this reagent is known to selectively reduce the C double bond O to the alcohol, and this is perhaps a good method to make allylic alcohol. Okay, you can consult the book of Carothers for this type of reactions. There is a detail on this type of reactions. Now, if you use palladium charcoal, then the C double bond will be untouched. It selectively reduces the double bonds. So over here, the conjugated and also the non-conjugated double bonds will be reduced, and it will form alkane. Okay. Now, for Na, ETOH, so none of these reagents we can see is giving us the desired product. Okay, because here all the double bonds are reduced when you use a BH3.THF. Here, selectively, the C double bond O is being reduced and the double bond conjugated is retained. So that is not also a product. Neither the palladium charcoal hydrogen will give us the target molecule. Now, when you are using sodium in presence of ethanol, please remember this is a condition for Birch reduction. So what happens over here? Sodium in presence of ethanol will give out an electron, that is a single electron transfer will happen. And here you can think that this double bond is now conjugated with the C double bond O. So one can think of a 1/4 type of addition of electron over here. Okay, that is called a single electron transfer. And this will generate a radical, and the double bond will shift over here, opening up the C double bond O and creating a minus. In conditions where ethanol is present, the O minus will get protonated and will give you this type of a enol. Further single electron transfer reaction will make this radical into a minus charge. Okay, where is it? Over here, as you can see. So this is basically over here we have a hydrogen. I have to mention that. So this is, here we have a, rather I should say this is a hydrogen over here. All right, and now tautomerization will take place and the enol will be getting converted to your ketone. Under these reaction conditions, what will happen? The ketone will be further reduced again by the single electron transfer method, and it will result in the formation of a alcohol as shown in the mechanism. So it is the Na in presence of ethanol which is going to give you Birch reduction, will give you the desired product over here. Okay, so our answer should be 2. That's a very easy question over here. We have to find out the components of adenosine methionine. Now, just one need to understand what is A, B, C, and D. If you can just remember the structures of the amino acids and the purine and the pyrimidine bases, then one can answer this question. Over here, A is methionine, B is cysteine, C is adenine, and D is uracil. Okay, so what will happen over here is that since it is saying S adenosyl methionine, that means this sulfur is getting coordinated to the adenine. So obviously we will say A and B will be present only. So our answer will be 1, and this is the structure of the molecule S adenosyl methionine. Okay. Now in the question number 37, this is rather a reaction related to carbocation formation and electrophilic addition reactions, related to electrophilic addition reactions, and also we will consider electrophilic aromatic substitution reactions. Let's see how this happens. So we have been given a double bond over here, and in presence of sulfuric acid, this will get protonated. So this is the mechanism. This is undergoing protonation. So we will say this is the electrophilic addition reaction taking place. So here, two types of carbocations can be formed. One having a plus charge here, and another having a plus charge here. Now, using the concept of hyperconjugation, we can say obviously, sir, that where there is a plus charge over here, that is 3 degree, and when the plus charge is over here, it is 1 degree. So obviously, this is more stable. All right. And now what happens over here, rather, is that the benzene ring will be making a attack to this electrophile. This is a potential electrophile. Okay. So that leads to the formation of this kind of a six-membered ring. And in the next step, what happens? Aromatization takes place. Okay. And we'll be giving you the desired product, which is 2. All right. Next. Again, a very simple question. The compounds that answers both, okay, will be haloform and Tollens test is. Now, for haloform reactions, we know there needs to be the presence of a ketomethyl group, and for the Tollens test, we need a CHO group. Okay, these are the two critical things that we need to remember. So this group is the will be undergoing haloform reaction, and this will be undergoing Tollens. So we got to look for these groups in the molecule. Does it have this? No. Does this one have? It has the ketomethyl group, but there is no aldehyde group. This one, we will say, see, this can be under the haloform reaction conditions, can be oxidized to a ketomethyl group. So obviously, this will respond to the haloform reaction. And since there is a aldehyde group, so also this will be responding to the Tollens test. So this 3 will be our answer. Why this is not going to respond? This is basically a lactone or a cyclic ester, and we know that esters do not undergo the Tollens or haloform reaction. Okay. Next. Over here, the question is the Hammett rho value for the following reaction is -2. The rate determining step we have to find out, is it A, B, C, or D? Now, whenever we have a Hammett value which is -2, that means in the transition state, okay, there is a development of positive charge next to this phenyl group. Okay, whenever we have a negative value, I repeat this, it means in the transition state, we are having positive charge generation next to this phenyl group. Okay, if the value increases to say about 4 or 5, then we will say there is a positive charge on the phenyl group. Okay, so this is the meaning of this Hammett value. Now, let's see over here, from first molecule to the intermediate one, which is step A, there is a simple protonation of the OH group, so this cannot be the case. Whereas in this step, in the second molecule or intermediate rather, from here this is going to the third one. Now this is also positive charge, and the next one is also positive charge. So obviously its transition state will also be having a positive charge. Okay. Now which means there is a possibility over here that the phenyl ring will be having a positive charge next to it. So what really happens, we will say that this step particular B, where when the OH2 is going away, at the same time the phenyl which is lying trans to this particular OH2 group will be migrating and coming to the nitrogen. In the due course of the process, the positive charge will be generated near to the phenyl group. So over here, step B will be our rate determining step. All right. And I hope that answers the query that you had. Next. Here, question number 40, we have to find out the correct order of energy for the following molecular orbitals. Okay. Now here we got to remember that more the number of nodes, higher is going to be the energy of the molecular orbital. So you just got to find out the nodes. Look at A. Here, this orbital is not in phase with this orbital. That means there is a node over here. This orbital is not in phase with this orbital, so there is a node over here. This one is not in phase with this one, so there is a node over it. So there are basically three nodes. Here, these two are in phase, but this one is not in phase with this one, so there is a node over here. Again, these two are in phase, so no node. This one is not in phase with this one, so there is a node over here. Again, this set is not, this particular orbital is not in phase with this one, so there is a node over here. So there are two nodes. So what we will say, A will be most high in energy, followed by C and followed by B. So our answer would be 3. Next, the question is from stereochemistry. The following hydrocarbon, which is a twistane, all right, we have to find out whether which of these following options is correct. Now, for a molecule like twistane, which is basically two, we can say cyclohexanes which are being fused together. Okay, just keep counting 1, 2, 3, 4, 5, and 6. So these are basically two cyclohexanes that have been fused together. Okay, this particular molecule, as I have shown over here with this arrow, if we follow, this is the C2 axis. Again, we have another C2 axis through this, and one C2 axis we can consider from, we're going right perpendicular to the molecule. So there is a C2 axis over here. C2 axis means that if you rotate the molecule by an angle of 180 degree, it generates the same molecule. So even though it is having 4 stereocenters, okay, it will only be showing 2 enantiomers. Okay, so over here we will say that it has a C2 axis of symmetry. Okay, it has a C2 axis of symmetry, but it also has a chiral axis. So over here the molecule will be chiral. Okay, next. Here we have been given in question number 42 to identify the major product formed in the photochemical reaction of a cyclooctane in presence of oxygen and a photosynthesizer. Photosynthesizers, you can think it can be a chlorophyll, it can be any dye like a eosine, Y, or a rhodamine B. Okay, these are your basically photosynthesizers which absorb light and convert them into chemical energy. Now, the options given over here are as follows. Now, in this particular reaction, we got to remember that a cyclooctane system can undergo cis-trans isomerism. Okay, so if you write the trans one over here, and if you place the oxygen the way I have placed, one can consider an ene type of reaction as I've shown. Okay, so this particular double bond will capture the hydrogen, and the CH bond will break and form a double bond, whereas this pi electron will go and capture the oxygen. All right, so keeping that in mind, so my molecule will now look something like this. Okay, now I got to only change the way I'm writing this molecule, and if I change it and make it flat, what I can see is this type of structure is generated, and so my answer will be 2. Over here, I'm not really agreeing with the answer that is being given. I still have reservations over it. So the major product formed in the following reaction, I think in the answer key sheet they have given 2 as the answer, but I think it is not correct. Over here, we got to consider NaOET as a base, okay, and we have to look for the acidic hydrogen. Okay, now having a close look, we can identify this particular carbon having CH protons to be acidic. Again, protons over here, there's one proton over here that also is going to be acidic. If you compare the acidity of these two protons, then what we will understand is that this will be more acidic for the simple reason that in a CO2 ET, there is a plus M effect from the OET group. Hence, it will stabilize less the carbon ion on the carbon, whereas a keto group will be having a greater stability. Okay. Hence, selectively, I will say that more and more carbon ions will be formed at this particular carbon. If that is the case, then one can think a minus charge or a carbon ion being generated over here, which can be conjugated with this. So one can do that resonance structure. Okay. Again, I'm thinking I missed. Hold on. I need to use the pen. Okay, I think the ET is missing over here. Yeah. So one can think that this can undergo resonance like this. That is what I was telling you. So this particular form can be resonance stabilized in this way. Whereas such stabilization will be hindered in cases of CO280 or lessened in case of CO280 because of the OAT group being present, which is making a donation to the carbonyl group. So that being the case, this can make now a simple nucleophilic attack to this particular chloride over here, and substitution will take place. And this should be our desired product. So according to me, the answer should be 3. However, in the answer key section, it has been given as 2.